Okay, so we saw this. ICA has many applications, and the basic idea is that you have multiple sources and you get multiple mixtures of signals from multiple sources, and you have to look at the mixtures, and on the mixtures we want to reconstruct the original signals. Right? And what are the key assumptions we make in order to unmix the signal? If the mixing matrix is known, so what you have is X is A times S. So this is N sources. This is the observed signal. Observed signals, right? N signals here observed. And A is the mixing matrix.
So in this, our focus is to find A or S or both?
Both. If we knew A, we can always invert it and we can find S. But the problem is we don't know A. So the question is, without knowing A and without knowing S, can we find A and S? And to do that, we have to make several key assumptions. One is statistical independence, which means that different sources in S, the N sources in S, are statistically independent. But that assumption, it turns out, is not enough. The other key assumption we make is that the sources in S are not Gaussian. They are non-Gaussian. And with these two assumptions, it turns out that we can unmix it, provided that you have more observations, more observed signals than the number of signals which are getting mixed. But for simplicity of mathematical exposition, we also assume that the mixing matrix is quasi and invertible, but is not really a restriction. As long as you have more observations, you have more signals than we are recording, then the number of sources, we are good. We can still do it. And some properties about, the rank of A matrix and things like that. But for this discussion, we'll just assume that it is quasi and invertible. Okay? Fine. So, what did you do last time? Does anybody remember? I forgot. Huh? Yeah, scaling, and that's all? Okay, so what we said is, what is X? X is a vector of n random variables, right? Is equal to A cross A into S. And this is observed. A is n cross n matrix and S is a vector of n random variables. Okay. So one assumption we made was E of Si, ith random variable in this matrix, is equal to 0. Right? That's one assumption we make. And this, let's say for all I, we make this. This is same as E of Xi equal to 0 for all I. Right? And why this is true? You can do it quickly, right? Yeah, so expectation of Xi is equal to Ai times S, expectation of that, and linear combination, which is Ai times expectation of S, which is 0, right? Because expectation of S is 0. Other way is also true. E of Xi equal to 0 implies E of Si equal to 0 for all I. And why is this the case? Because, why do we do this? Because we assume, even if we observe some data X, we don't know S. So, if X has non-zero mean, we scale the X. We center the X. We subtract this respective means. From there, and we make E of Xi equal to 0. And this makes sure that E of Si is also equal to 0. And so since X is A times S, and we assume A is invertible, this implies S is A inverse X. So now expectation of S is A inverse expectation of X, which is equal to 0, right, for all the things. So therefore, even if your original sources have some means, if we center the observed variables, then that also centers them. And that does not change the matrix A. So that's one thing. Second, we saw ambiguities because of scaling. Right? What you could do is, you can scale up A and scale down S, and that leads to ambiguities. So we have to resolve it. So we make the second assumption, which is E of Si squared equal to 1. Right? So that's the assumption we make, and that's not really a problem, because even if those sources were having big variances, you can absorb them in the mixing matrix. You can just, we are not really interested in the absolute magnitude of different sources. We just want to look at the patterns there. So that's not a problem. And in reality, we don't know S. So we observe X. So in reality, X. So what we also do is we scale the X. We scale X such that E of Xi square equal to 1, or variance of Xi equal to 1 for all I, and that's also for convenience. So what we know is, and that's also not a problem because we can absorb that in the matrix A. So we know that X is equal to A times S. If we scale X prime as D times X, right, some diagonal matrix, so this means this is nothing but D times A times S. And now when we do the blind source separation, instead of estimating A, we will estimate D times A. Right? Everything else stays the same. So basically you are just scaling the rows of the matrix A suitably. So this is what we estimate. And if you are really interested in A, you already know what D is because you know how you scale the X. So you can use that D to get the actual A. Okay. Okay, so now the question is,
in scaling of X, ensuring that E of Si square is 1.
No. Scaling of X means E of Xi square equal to 1.
Xi square.
Yeah. Not Si square. No. So this is what we assume. We assume that E of Si square is 1, but we also make sure that E of Xi square is 1. This is just convenience. Right? So when we talk about independent component analysis, why not only statistical independence? Why do we need to do more? Oops. Did I open the right one? Yeah. Okay. So let's assume just independence and see what we can get. Okay? So what do we mean by independence? What do you mean by independence? So assume, let's say, S is independent. What this means is Si, Sj are independent for all I not equal to j. Right? That's what it means. And I less than equal to n. So independence is in general very complicated thing because we cannot even find independence in the true sense. But a proxy for independence. What does independence imply? The covariance equal to 0. So what does this imply? This implies expectation of S transpose. Right? Now S is now not numbers but random variables. S transpose gives you a matrix of pairs of random variables, products of pairs of random variables.
Also. S is scale. S will be scale by subtracting the mean and mode.
Yeah, we already assume all of that. So it has unit variance and zero mean. So what does this imply? If S is independent, E of S transpose is?
Covariance like this for S.
Yeah, but if S is independent? Diagonal, right? It's an identity matrix is equal to I. So this implies E of S transpose equal to I. Fine? Okay. So now let's look at our problem. We have x equal to AS. We don't know what A is, we don't know what S is. And x has been normalized to zero mean unit variance. And S we assume to be zero mean unit variance. So what does this imply? S equal to A inverse times X. We already assumed A is invertible. Right? In order to get the sources, what does this mean? I need to find a matrix A inverse. Let's call it the matrix V. Right? So this implies find a matrix V such that V times X is independent. Right? We are all interested in independence of the sources. What do you mean by V times X? V is a matrix, X is a vector of random variables. So each row, V times X will be a vector of random variables. Each vector will be linear combinations of the random variables in X. So you want to find a matrix V such that Vx is independent. What does this mean? This is nothing but expectation of, what does it mean to say V of X is independent? Expectation of Vx transpose equal to I. Right? That's what we want. What does it give me? Expectation of Vx X transpose V transpose equal to I. I've already know the observations X. I've already normalized them to zero mean unit variance. Now I want to find a vector or matrix V so that this is true. Now who can give me this matrix? So this is called white. This implies S is white, just a technical term. Right? Now if you look at X transpose will not have I, expected value of X transpose will not be I. So this is nothing but, I can write it because linearity of expectation, this is nothing but V times expectation of X transpose V transpose. Linearity of expectation. Okay. So the matrix X, the data that you observe, will not have, non-zero, will have non-zero covariances across different variables. And I want to find a transformation V, a linear transformation V, which will whiten them, such that XV is white. Right? This is what we mean by this is white. Right? S is white means expectation of SS transpose is I. Similarly, we observed X, and X is not white, maybe it's pink or something like that. And we want to find a matrix V such that when we multiply X with V, it becomes white. Right? That is if only we use independence. How do we do this? Right? So that's my problem. I have to find a matrix V such that X transpose is white. So let's say C is expectation of X transpose, right? Is the covariance matrix. So one approach to do that, can anybody guess? How do we do this? We have done this. Just have to think a little bit.
So do what? To find C.
Find V such that this thing happens. The one that we have written here happens. So, okay, before we go there, how do you find C? Let's look at C. How do you find C? How to estimate C?
So we have X, right? So
What is X? X is a random variable. But we also have observations of each of those random variables, right? So, let's say X cap. X is actually a vector of random variables, right? Vector of size n. Let's define X cap as a matrix of observations, the realization of the random variable. How can I write it as? X1, 1, X1, 2, and let's say we have observations for t time instance, right? X2, 1, X2, 2, all the way till X2, t. And then Xn, 1, Xn, 2, all the way to Xn, t. Fine? So that's my matrix X cap. And I've already centered that, right? I've already subtracted the mean and the variance. I set equal to 1. I scaled this such that this is true because I want the mean of each of those random variables to be 1. Okay? So what is my estimate of C? Let's say C hat, which is an estimator of C. What's a good estimator of C? Sample mean of? Not sample mean. Sample mean of X cap is 0 because I already normalized this. X cap into X cap transpose. And do I need any normalizations? 1 upon n minus 1? Or I've already assumed that this variance is equal to 1, right? So n upon n minus 1 probably, right? To get an unbiased estimator. Right? Okay, so I have an estimate for C now. Now I want to find so let's say, this is one way to find the estimator of C, but let's start with the C. Right? What will be the property of C? Property, I'll not prove it, but any such matrix C will be symmetric and positive semi-definite. Okay? So if any matrix is symmetric, positive, semi-definite, this implies, I'm again not going to prove it, but we just state it. It can be factorized at E D E transpose, where E is the matrix containing eigenvectors eigenvectors of C, and D is corresponding diagonal matrix. With eigenvalues. Okay. So let's say you can do that. Let's say I grant you that given this matrix C, you can factorize it using eigenvalues into this. Okay? Now can you whiten X? What do you want? V times C times V transpose is equal to I, right? V C V transpose equal to, I. Okay. Fine. So how do we do this? Now your C is E D E transpose. And what do I want? V C V transpose equal to I. What should the value of V be? Such that V C V transpose equal to I. No one is there? Huh? So V equal to E D to the power minus 1 by 2. What does this mean? You take square root of the eigenvalues and do 1 by square root of the eigenvalues in the diagonal. Okay? Times E transpose. Let's check. Let's check whether this does it or not. So VC V transpose is E D to the power minus 1 by 2 E transpose. And now I put the value of C, which is E D E transpose, and I put value of V again. Okay, and E is a complete matrix of all the eigenvectors. So E transpose E becomes equal to sorry. Yes, thank you. Transpose, okay. But it is symmetric, so it will stay the same, which is same as this thing, right? So now E transpose E becomes I. This E transpose E becomes I. Then this D to the power minus 1 by 2, D to the power minus 1 by 2 times D becomes I. Right? So E times E transpose.
Is it like D into D minus half is I? How can we do this?
Just work it out. Just multiply two diagonal matrices. You will just have the diagonals in the. Both are diagonal matrices. Right? So this is nothing but I. Okay? But there's something more interesting that's going on here. So we are saying that we are decomposing C using eigenvalues. But my matrix C, an estimator of that, is given by this matrix X. Right? Can we relate e to something that we know about x or something we can do for x. We've done FED, so yeah, let's try to relate that. So my x cap is, so yeah, my c cap is equal to x cap transpose, right? Let's say I do SVD of x cap, exact XVD, right? Not approximate, but exact. So how can I write it as u lambda v transpose, right? So what is my x cap times x cap transpose? U lambda v transpose times v lambda u transpose. So v transpose cancels out, so this becomes u lambda squared u transpose. And here what we did to see, we factorize using eigenvalues, right? E d E transpose. Right? So my u is essentially E, and my lambda is basically lambda square is d. Lambda is square root of d. Right? So what is it giving me? If I factorize like this, so what's my vector v? What's my so my whitening matrix W E d to the power minus 1 by 2 E transpose, right? Which is nothing but u lambda to the power minus 1 u transpose, right? Where u is the SVD of x cap, right? The vector corresponding to the.
So this W same as V?
Yes, I am not using v because here I've used v, so it's kind of, it might confuse you guys. But yeah, so this is a W. So now what can we say? That W times x is white. Okay. So basically, what am I doing? I am actually doing the PCA. Right? If I just assume that my components are independent, then one way of finding those independent components is through PCA. Right? But what is the problem with PCA? Why can't we use it?
There's also in C cap, I will not normalize those terms, like n upon n minus 1.
That is just a scaling factor, so generally they don't really matter that much. We just normalize all the rows to have is unit variance and
Because
say
if
the
you
V.
normalize earlier, then we don't need to multiply n into n minus 1.
You normalize with n minus 1 instead of n, so then you're fine. Yeah. If you divide by n, then you're 2. And even if it's just a scaling factor, so scaling factors don't really matter. Here we are looking at the actual vectors, right? So then it doesn't matter that much. Okay? So, fine. Okay, so this is how we can find. But the question is, so what have we done? I have x equal to a times s with all my assumptions, and expectation of x transpose is not equal to I. So I found a matrix W. What should I use? Or let me use V only. This V is different from that, right? So it's a mess. But
Basically,
anyway.
V subscript I, something like that.
Yeah,
Independent.
VW or something like that. So I found whitening matrix VW such that is white, right? So this implies, if I look at this implies my S is equal to A inverse X. Okay. So typically when we do ICA, as a first step we do the normalization, the second step we do the whitening. So we multiply X with this vector so that it's with this matrix so that it becomes white. And this is called the whitening step. So let's say, my Z equal to this whitening matrix times X. Okay. So this becomes VWAS. And this may not be the inverse of A. Or this matrix that will whiten X is not unique. There can be many different whitening matrices. Okay. So
VW is the whitening matrix for S. What's the whitening matrix here? VW.
No, ignore this. So VW is the whitening matrix, right? We observed X, we multiplied it with whitening matrix. Now my expectation of XX transpose becomes equal to I, right? But this whitening matrix VW is not unique. There can be many such. So we have shown you one method of finding the whitening matrix is through PCA or through SVD. But this is not the only method. You can find other ways to do whitening matrix. Can somebody show this? Let's say I construct Z prime equal to U times Z, where U is orthonormal. Okay? So clearly Z prime is not same as Z. I can do any transformation, any orthogonal transformation. What is expectation of Z prime transpose? Right? Which is expectation of U, Z transpose, U transpose, right? By linearity of expectation, this is U times expectation of Z transpose, U transpose, right? Expectation of Z transpose is I. So this is U times I times U transpose, which is I. Right? So what is happening? Even if I whiten it, this whitened matrix or whitened variable Z, I can multiply it with any orthogonal transformation, any orthonormal matrix, and it'll still be white. So therefore it is not unique. There can be many ways of doing it. So therefore it does not give us a way to separate those components. Right? Whitening is just one step, but it is not complete. Right? So we need to do something else. Okay, so what do we do now? So if we have whitened X and converted it to Z, then any matrix, I want to now find Okay, let's do it a little slowly. So what do I have? My x was equal to a times s. I whitened it. This means I get z equal to whitening matrix times x. Which is VW times A times S. And this VW may not be A inverse, right? There are many such matrices. So I still want to find A inverse, right? What do I want to find? So, yeah, so if Z is equal to this, I have to multiply it with the inverse of this matrix to get back S. What does this mean? S is equal to VWA inverse times Z okay. Let me use the same Z. So I've given the data A, I normalize the data, I whitened the data to Z. Given the data X, I normalized X and I whitened it to Z. Now I want to find this matrix which will give me the sources. So I want to find W so that WZ equal to S. So what all possible matrices W I can use, right? What are the possibilities? What are the valid matrices that can have this property? Right? So in order to do this, let's look at expectation of S transpose is same as expectation of WZ transpose. Actually it's all capital. Okay, fine. I already assumed that my source matrix is white. So what is the left hand side? Is identity. Right hand side by linearity of expectation, what do I get? E of Z transpose times W transpose. I've already whitened X to Z. Right? So what is E of Z transpose? I. So this becomes W transpose. So now after I whitened the data, I have to find a matrix W so that W transpose is I. So W has to be only an orthonormal matrix. So once I have whitened my data, once I have normalized and whitened my data, all I need to find is an orthonormal matrix W such that WZ becomes equal to S. Yeah, so that's the only task left before us now. And that's where we need the non-Gaussianity. Because now you can think of it, as WZ equal to S, so Z equal to W transpose S. What does this mean? I have these multiple sources and they are mixing, they are getting mixed according to these components. And if we can somehow quantify, right? We assume each of these sources are non-Gaussian. Right? We assume each of those sources are non-Gaussian. And if we can somehow measure non-Gaussianity, right? How much non-Gaussian they are, if we can somehow measure that. Right? If we can give a formula for measuring the amount of non-Gaussianity, then Z will essentially get mixed. Several non-Gaussian sources are getting mixed. Therefore, the Gaussianity of Z will be higher than that of S. Now we want to find a W such that WZ equal to S. So we look at W that maximizes the non-Gaussianity of W times Z. And that is going to give us S. So all we need to do now is define a measure of non-Gaussianity, and there are several measures that people have used. We are going to in the class use a measure called kurtosis, and then just optimize. Find a W such that the non-Gaussianity of W times Z is maximized. And this gives me the ICA. And then you can use other measures also. So we'll stop here, continue next time. Thank you. Today what we are going to discuss is how do we separate the sources. So yeah, last time we discussed that just independence is not enough. If you just use independence of the sources, then there can be many solutions. There can be many solutions, each of them transformed by an orthogonal also normal matrix, right? But now when we assume non-Gaussianity, then we can separate it. In addition to independence, if we assume non-Gaussianity of the sources, then we can separate it. And today what we are going to discuss is a measure of non-Gaussianity called kurtosis. Right? So how does a Gaussian distribution look like? This is like X, this is P of X. You get a bell-shaped curve peaked around the mean or something like this. Now we are given another distribution. When can we say it is not Gaussian, right? So we standardize the distribution, we make it zero mean unit variance, right? And if it's a Gaussian distribution, it will overlap exactly on this, because all Gaussians are parameterized by just two parameters. But if it's a non-Gaussian distribution, it can be slightly different, right? So the different, it can be something like this. So this is what is called, this is a Laplace distribution, right? And this is Laplace, and this one is Gaussian or normal, right? And what is Laplace distribution? P of X is some normalizing term e to the power minus x minus mu by some variable, or let me not use the word mu here. Let me use a and b. X minus a divided by b, absolute value. Right? So in Gaussian we have square. In Laplace we just take the absolute value. Okay, so this is Laplace distribution. Okay, so what happens with Laplace? So when we are here, you can see that the probability values are kind of lower. But if you look at the tails towards the extreme right or the extreme left, right, when x is either very big or very small, then which of them will be higher? The Laplace distribution or the Gaussian or normal? Which of them will have a higher PDF value? Laplace, because it is e to the power minus x. Let's say a is 0, b is 1. So e to the power minus x, and Gaussian e to the power minus x squared. So Laplace will be higher. So these are, they have a heavier tail. So these are called the tails of the distribution. These are the tails. And therefore these distributions, such distributions are called super Gaussian. And you can look at a uniform distribution. Now if I look at the tails, uniform has zero tail actually. It's just restricted to the range A and B. So this is an example of what is called a sub-Gaussian. So this is uniform, and this is normal again. Okay. So with this, can you figure out a metric for measuring the Gaussianity? How do you measure Gaussianity or some element of Gaussianity? Because once we come up with a measure of Gaussianity, we are done. Why? Then the algorithm becomes very clear. Right? So, are you all convinced that once we know the measure of non-Gaussianity, we are done? We can come up with an algorithm? Let's see. So, what is our problem? We have normalized x, right? And we represent x as as, and then we whiten x, we represent z as vw times x, right? Now, what is my problem? So, let's say z equal to, let me just use v now because the context is different. So, where and our x equal to as, fine. So, this is whitened. Right. So, what do you mean by whitened? Expectation of z transpose is equal to I. What's my problem now? Find W such that W is orthonormal and secondly WZ has maximum non-Gaussianity. So if we have a measure to measure non-Gaussianity, what is the key idea here? That my signal S is non-Gaussian, and if I look at the signal Z, Z is a linear combination of S, various components of S's. Now, and by law of large numbers, even if I mix two components which are non-Gaussian, the mixture is going to become more Gaussian-like. So once I have the mixture, I want to separate them, so I want to find this matrix X. So this will give me several components, and I want to choose a matrix W such that the non-Gaussianity in those components is maximized. So if I can choose W so that this is orthonormal, that we showed last time, it has to be orthonormal after normalization, after whitening, then the only, and this ensures, orthonormality ensures that S remains independent, the discovered S remains independent. The only thing we have to make sure is that W times Z is maximally non-Gaussian. Right? So once we define the measure of non-Gaussianity, we can formulate it as a constraint optimization problem. Maximize over W non-Gaussianity of W times Z, subject to the constraint that W is normal, also normal. Right? And there are several measures people have used. Yeah.
We are the assumption that S has maximum non-Gaussianity of Y versus Z.
No. We only assume X is non-Gaussian.
S.
Yeah. We only assume S is non-Gaussian. Now,
But we are trying to get WZ of maximum non-Gaussianity.
yes. So, okay. So let's put it. So now we want to find W. That's a very good question. I think it's very important. So let's say we want to find WZ, right? So let's call this Y. Okay? Or let me just look at just one component. Let's say Y1 equal to W1 times Z. Just to simplify this. Yeah, so this is the first row. W1 is the first row of W. So I get Y1. So now I put it, the value of Z, which is W1 VAS. Okay. Now this I can write. So let me write this as matrix Q1 or vector Q1. Right? I combine these three terms and write it as Q1 times S. Okay. So this is nothing but Q1J Sj summation j is going from 1 to n. Okay. I am finding w. I am explicitly choosing a w, but it is leading me to some q's. Right? I don't know what a is. I know what v is, but I don't know what a is, so I don't know what q's are. But no matter what w I choose, it's going to give me a q. Right? In other words, so this is y1. Whatever y1 I get, that y1 will be a linear combination of s1 till sn. Right? All those independent signals. Right? If each of those sj's are non-Gaussian, each of them is a non-Gaussian. Right? They may be slightly non-Gaussian. Right? They may be Gaussian with slight shift. And some of them may be highly non-Gaussian. Doesn't matter. Let's say I find W such that these Q's are not, just one of them is not 1. Right? So I find a W let's say I choose a W1. Let's say I have a measure of non-Gaussianity. So for every source I choose I have a measure of non-Gaussianity. Right? So for S1 I have some non-Gaussianity and so on. So if I was to maximize W1, I was to choose W1 such that the non-Gaussianity in Y is minimum. So it's maximum. Non-Gaussianity is Y1 is maximum. What will the corresponding Q1s be? Are you understanding my question? No. Okay, let's make it slightly simple. So let's make it n equal to 2. So my y1 is q1 s1 plus q2 s2. I'm not choosing q1 and q2. I'm choosing w1s and w2s. Right? But it will lead to, because I know they are linear combinations, it will lead to corresponding q1s and q2s. So what choice of q1 and q2 will maximize the non-Gaussianity in y1? So let's say there is a measure called kurtosis, right? And that's a measure of non-Gaussianity. It is 0 when the signal is Gaussian, and it is non-zero when it is non-Gaussian. Okay? Let's say there is a measure like that. So let's say kurt of S1 is 5. Kurt of, let's look at the simple case first. S2 is also 5. Let's say both have equal non-Gaussianity. Right? And we also have the constraint that expectation of y1, or not expectation is 0, but variance of y1 equal to 1. Right? So this constraint actually implies q1 squared plus q2 squared equal to 1. Okay? So I'm combining the signal subject to that constraint that variance of y1 is equal to 1. Okay? So I mean the reason I need to do that is otherwise we'll just do a simple scaling, right? That's not what I'm interested in. So the question is, if you combine these two in any proportion other than either a 0, 1 or a 1, 0, what's going to happen to the non-Gaussianity of the mixture? If your Q1 is 1 and Q2 is 0, right? Then the non-Gaussianity of Y1 will be the same as that of S1, which will be equal to 5. If you have any other proportion, then you are mixing two non-Gaussian signals. And by central limit theorem, the result is going to be more Gaussian than either of those two signals. These are two signals which have equal non-Gaussianity, right? So any other choice of Q which is not either 0, 1 or 1, 0, you will have higher non-Gaussianity lower non-Gaussianity for Y1. So therefore the choice of W that you will choose will necessarily force Q1 and Q2s to be either 1, 0 or 0, 1. Right? Now let's take the other example that, let's say this non-Gaussianity was 10 and this non-Gaussianity was 5. Now you combine these two in some proportion. The resulting non-Gaussianity will be less than the max of the two. Right? This has a non-Gaussianity of 10. You mix it with another signal with non-Gaussianity of 5. It may be somewhere in between. It's certainly going to be that less than 10. So that will not minimize my objective function for y1 because I can have a choice of setting q1 equal to 1 by choosing my w appropriately. I don't know what the mixing matrices are, but I can choose a w. q1 equal to 1 will translate into some value of w. And those value of w I can select. And that is going to actually unmix the signal and therefore maximize the non-Gaussianity. Right? So that's the key idea in ICA. Two key assumptions, independence and non-Gaussianity. If you just use independence, then PCA also does the same thing, except that, there are many choices. PCA is only one of the choices. I can do many ways of whitening the signal. So in top of that, if I use a measure of non-Gaussianity, then I have this and I can do that. So now what's the measure of non-Gaussianity?
In that, y1 is already S1. Y1 is S1 by definition only.
No, y1 is not S1.
So W is S.
Huh? No, I want to find a W such that WZA equal to S. So so S is the unknown signal, A is the unknown mixing matrix. So this is unknown. And this is also unknown. But this is known. This is a known observation. I can whiten it. So this is also known. After whitening, I have converted X into Z. All I know is Z has covariance of Z transpose equal to 1. All the components are independent in Z. But that not necessarily mean that it actually represents S. So I want to find a W such that WZ becomes equal to S. But I want to find. I don't know what S is. I want to find.
So then y1 will be S1.
If I optimize W such that this maximizes the non-Gaussianity, then y1 will be equal to S1. We'll choose a W such that y1 equal to S1.
So like in that case, I said aim is that we get y1 to be S1. But
Yes.
if, for example, cut of S2 was 10 and cut of S1 was 5,
Mm-hmm.
then it would imply that y1 will be S2.
Yes.
So
Yes.
how? But that was not our objective initially. So how will the map?
No, our objective is to separate them. See, remember we talked about we are still invariant with respect to permutations. There were two invariants, right? One is the scaling. That we take care by just making the norms equal to 1. Second was plus minus 1. That stays. So your y may be equal to minus of S1. And it will still work. It will still give you the same maximum kurtosis, right? Maximum non-Gaussianity it will still give. So that you will not be able to distinguish. Either you will get S1 or you will get minus S1. Or you can get any of the components. It need not be in the same order.
But what I was saying is that if they are y1 to yn,
Uh-huh.
and there everyone is q1 summation of qi si.
Yeah.
But one si will be maximum of all.
Yeah, so now the way you do that is you first find W1 subject to these constraints such that your non-Gaussianity is maximum. This will give you in this particular case S1. Then you find W2 such that then you subtract W1 from that, from the Z. So then you find W2 such that the new signal is also orthogonal. It is also independent of that, right? So independent of the first signal, the second signal that you get, and then with that constraint you maximize the non-Gaussianity. Because first signal you already recovered. And then when you do the third signal, you put the constraint that, it should be independent, it should be, orthogonal to the first and second signals. And subject to that constraint, you find W's which maximize the non-Gaussianity. And this is only one measure. Okay, so let's see. Let's just do that. So kurtosis is inspired by looking at the tails of the distribution, right? And it gives more weightage to the tails. So let's formally define what kurtosis is. Kurtosis of any random variable x is E expectation of x to the power 4 minus 3 times expectation of x squared squared. Right? So if E of x squared equal to 1, we are assuming 0 mean, and if variance is also 1, then E of x to the power 4 minus 3. Okay? So you can see that this kurtosis measure is doing e to the x to the power 4. So distributions which have a heavier tail than Gaussian will tend to have higher kurtosis, and distributions which have a lighter tail than Gaussian will tend to have a kurtosis which is smaller. And it turns out that kurtosis of a Gaussian, if x is distributed according to Gaussian, normal with, let's say, 0 mean and sigma anything, right? So that we can show, that you can just elementary mathematics, just do the integration and you can show that. So Gaussian random variables have 0 kurtosis, and a variable is super Gaussian. It's called super Gaussian if its kurtosis is greater than 0, and the variable is sub Gaussian if the kurtosis is less than 1. So x is k of x is greater than 0 is sub Gaussian if k of x is less than 0. Fine. So the measure we use is the absolute value of kurtosis. Right? And that's the measure that we maximize. And you can also show if x1, okay, so then I keep that as a homework exercises, right? So this is let's say homework 1. Prove. Okay. Kurtosis is x. If x is distributed according to Gaussian, then kurtosis is 0. If x1 and x2 are independent, then kurtosis of x1 plus x2 equal to kurtosis of x1 plus, right? So let's say this is homework 2. This, I think, elementary. Kurtosis of alpha x is equal to alpha to the power 4 kurtosis of x. Right? These are the properties you can then show. These are simple properties of kurtosis. Right? Yeah. So now what's my algorithm now? And there are other measures also. Neg entropy is another measure that you can use. And also there are research, people have done methods where so far we are ignoring the time dimension of the signal. We are just assuming each of sample is independent, and we are not really looking at the dependence across the time. But you can create a measure of non-Gaussianity by looking at the dependence across the time also. Right? So that kind of non-Gaussianity you can incorporate in the models here, and then your objective function will be slightly different. Right? Instead of maximizing kurtosis, you will maximize some other measure. Okay, so what is the algorithm for ICA? Input xit for I in 1 to n and T in that's my signal. Output ID SIT for same and mixing matrix A n cross n, right? Such that or let me not do mixing matrix, let me do W. Is approximately equal to S. W is approximately equal to A inverse. Okay. And once I've got the mixing matrix, I can actually, once I get the W, let me call it unmixing matrix. Okay. Once I get W, then I can always construct S on that. Okay. So how do I do this? So now we have pretty much everything, right? We have to just put it together. So, step 1, normalization. Right? So you have x tilde such that E of x tilde equal to 0 and variance of x tilde equal to 1. Right? That's step 1. Then step 2, what do? Whitening. Right? That means find U such that, or what did we use? V we use, no? Such that expectation of V x tilde into V x tilde transpose, right, equal to I, which is what? Nothing but V expectation of x tilde transpose V transpose equal to I. Okay? Step 3. So let Z equal to V times x tilde. Now what I wish to do? Use capital Z. Okay. So what do I wish to do now? Repeat. Find or you know what? Right, so I maximize, I find a linear combination that maximizes, and W transpose Z is independent of previous components. I can do for I equal to 1 to n. Right? So every time I find a component which maximizes the kurtosis subject to these two constraints. First constraint is that the variance of, so the sum of the squares of Wj's is equal to 1, and the component that I find must be independent of the previously found components. You can translate that into correlations, right? So what is this? What does this mean? So if I create the matrix X from the data, then the correlation of W transpose Z with all the previous components, the dot product is equal to 0. Fine. Any questions? So let's look at some examples just very quickly. So this is a distribution in 2 dimensions. P of Si is uniform in the 2 dimensions. So uniform distribution is a non-Gaussian distribution, right? Now if you mix it with this matrix 2, 3, 2, 3 and 2, 1, right? So the first component you get is twice the first S and the 3 times the second one, right? And similarly 2, 1, you again get 2 random variables, right? So here what you are seeing is the distribution of these random variables, or just some samples of these random variables. Once you mix it with this matrix, the distribution changes to this now, right? Because now the maximum value that you can get is when these things are both 1. So 2 plus 3, 5, which you'll get here, right? When both are 1. So that's the new distribution of the pairs of random variables. And it looks like if you have this distribution, you should be able to recover the squares, right? The actual distributions, because if you knew that this was uniform distribution, then you should be able to recover. You can just look at these lines, and from these lines you can figure out the weights of the mixing matrix. So that's same idea in a different way. How does IC recover the components? Contrast it with a Gaussian distribution. Right? If you have a Gaussian distribution, this thing will look like this. And now if you mix this with the same mixing matrix, the distribution will still look like that. There's nothing will change, because sum of 2 Gaussians is a Gaussian. So if the distribution doesn't change, there is absolutely no way you can figure out the original components of the distribution. Okay, so this we have done, this we have done, kurtosis we have done. We've done sub and super Gaussians. Okay, so this is again pictorially. So this is a plot of, let's say this is Q1, this is Q2. So this is Q1 squared plus Q2 squared equal to 1, right? This is a set of points where Q1 squared plus Q2 squared equal to 1. Right? And now these are the points, this is the kurtosis of Q1S1 plus Q2S2. Assuming that S1 kurtosis of S1 and S2 are the same. So this is how. So what is Yeah. So when we are choosing the weight vectors, we are combining them in this way. And this I can write. So S1 and S2 are independent of each other. Right? So this I can write as nothing but Q1 to the power 4 kurtosis of S1 plus Q2 to the power 4 kurtosis of S2. Right? And assuming those two kurtoses are the same, how does this function behave? Right? Subject to the constraint Q1 squared plus Q2 squared equal to 1. And this is, these curves here, these squarish type curves, these are the plot of these functions. Okay? Subject to the constraint that, no wait, I'm sorry. Kurtosis of this is constant. So the square brackets are the terms where the kurtosis of this term is constant. And the circle is the one where Q1 squared plus Q2 squared is equal to constant. So if I was to grow the kurtosis, I will grow this square. But I want to keep this constraint also. So what is the maximum I can grow this square while not violating this constraint? What will that point be? If I make square too big, then all the points in my square will have different values of Q1s and Q2s, but they're all bigger than 1. So this square is ruled out. So what is the maximum value of kurtosis I will get? Is when this square is circumscribing the circle. Right? Now here when it is circumscribing the circle, what are the points of optimality? They are identical to the axis locations. Right? So this point, this point, this point. So these are the 4 points that maximize my kurtosis, and they correspond exactly to Q1 equal to plus minus 1 or Q2 equal to plus minus 1. So this is again pictorially showing that how kurtosis maximizes the non-Gaussianity and actually helps you to recover the components.
Then in the algorithm, we have not ensured that W will be also normal. We have only ensured QJ square is.
But that will ensure, right? If you ensure that the recovered components are orthogonal, then W's will also be orthogonal.
But we had done something Wj square is 1, but that could happen in other cases also. If it is not, W is not high.
This constraint, right?
Above
No, this is fine.
number 1.
Yeah.
Wj square solution is 1.
Yes.
But that can happen otherwise also. Like, but the constraint is that WB transpose is high, right?
Yeah.
WI transpose WJ.
Over here.
Yeah, so there are 2 parts of this constraint. One is this part, which is the diagonal entries are 1.
WJJ.
Yeah. So this is ensured by this constraint. Right?
But that every entry is 1. That will be n.
No, not Wj. W transpose W. The diagonal of W transpose W would be equal to 1. And there are 2 parts of it, right? One is the diagonal entries are 1, and the other part is the off diagonal entries are 0. So this constraint ensures that the diagonal entries are 1. Here W is a vector, it's not a matrix, right? We are doing it one component by one component. And this constraint ensures that the dot product of the off diagonal entries is equal to 0. So your Z is B A S, okay? And we find W1 such that W1 transpose Z. Let's say we find W1 and W2, right? Such that W1 transpose W1 equal to 1. W2 transpose W2 equal to 1. Okay? Fine. That's the summation Wi squared constraint. Okay. So now consider this matrix W. Fine. So these are columns of W1. So what is W transpose Z? That's what we are finding, which is W transpose VAS. Okay. Now this we want the components to be orthogonal, right? So let's call this Y. So we want expectation of Y transpose equal to I. Right? That's what we want. What does this mean? This implies expectation of W transpose VAS transpose equal to I. Right? So what is this? W transpose VA expectation of S transpose. Now I take transpose A transpose V W. Right? This is equal to I. Right? I just So this is already I. No, but I don't think we have to do it like that. Wait. No, this is going to lead to problems. I'm going to write it as expectation of W transpose Z. I've already whitened it, right? Fine. I've already whitened Z, right? So, but the component had recovered, that should also be whitened. So what does this mean? Z expectation, W transpose W equal to I. I've already whitened, so this is I. This implies W transpose W equal to I. So W is also normal. Okay. So these are equivalents, right? Either I can say that W are orthogonal, or I can say that the component that I've recovered, they're orthogonal. It amounts to the same thing.
So can you go back to the page where you wrote the confusion?
Yeah.
So in this, the second part you are saying that W transpose Z is independent of previous components. So that means the dot product is 0.
Yeah.
So that is.
I mean, see, I'm abusing a notation a bit. Here Z is a random variable. You can also think of it as, observations. So, little bit. So, yeah. So, random variables are independent. That could also, we are using a correlation as a proxy to that. So, what does that imply? That the correlation of the observations that you get, the dot product of observations, since we have already made them unit norm and zero mean, then the dot product of those specific observations, Z1 and Z2, that they are 0. So that's what we are trying to do. So I wanted to do k-means. I wanted to start on k-means today. I didn't get time. But there were some questions about assignments. There will be one final assignment, 5 marks, which is the k-means. It's very simple. I was planning to give you an assignment on ICA, but we are not giving you an ICA assignment. We are giving you k-means assignment. So in the next class, we'll take a detour from the matrix factorization algorithms. We'll cover k-means and then come back to non-negative matrix factorizations. Right? So that you can do the assignment. Hopefully it will be released today or tomorrow. And your assignment deadline has been extended. That has been communicated to you. Right? That has been communicated. But the new assignment is not out yet.
So what is the final deadline? 7?
Whatever they have announced. 7th, I think so. Yeah. So just add 7 to the. But then one assignment will also come out and you have to do everything together by that deadline.